Nuclear magnetic resonance spectroscopy, NMR. NMR is an instrumental technique that is used to identify the structure of organic molecule. In this technique, the different molecule can be put in a magnetic field where the spinning nuclei of these molecules will interact with radio waves and absorb energy from the radio waves. Not all the nuclei will have that spin and will absorb radiation. Only certain nuclei will achieve that. And these nuclei are the ones which have an odd mass number, or if the number of neutrons plus the number of protons is odd. The nucleus then will have a spin. So something like proton or hydrogen with 1 will have a spin, while deuterium, which has a mass number of 2, will not have a spin and will not absorb radiation or give a signal in NMR. Also, carbon 13 will have a spin, while carbon 12 will not and will not give you a signal. So how does it work? So these nuclei act like small magnets and they tend to spin. They have a spin, and in the absence of an external magnetic field, this spinning is random. They have random orientation and they tend to cancel each other out. However, in the presence of an external magnetic field, they will start to orient themselves, their spinning direction, either with the direction of the external magnetic field or opposite to the external magnetic field. There is a difference in the energy between these two states, the arrangement with and opposite. And if we subject these nuclei to radio waves, then they can absorb the energy from the radio waves, and the energy will be enough for these nuclei to flip and to arrange themselves opposite to the external magnetic field. So the amount of energy that is absorbed from the radio waves can then be recorded and can be interpreted as a signal that will give us information about these nuclei and their chemical environment. So how do we do the NMR measurement? So you have your sample and then you place the sample in a certain magnetic field using a strong magnet. And then there is a radio frequency radiation which is emitted onto the sample. And then the sample, if you have the sample as a solid, then you need to dissolve it in a certain solvent. And that solvent must be chemically inert, or at least it will just dissolve your solid and will not interact or will not interfere with your spectrum. This is why something like deuterated chloroform is a good solvent for NMR, for proton NMR, because now they have replaced the hydrogen in the deuterated in the chloroform with deuterium, which will not give you a signal. Also, you could use something like carbon tetrachloride, which doesn't have a proton at all. So it doesn't actually interfere at all with your spectrum. All the signals are used in reference to a certain reference material or a standard. This is called the tetramethylsilane, where tetramethylsilane is added to your sample to provide a reference signal. The spectrum at the end can be integrated to find the relative peak heights. So the signals are given a name called the chemical shift, which is on the x-axis here, and each different proton will give you a different value. The reference substance, which is tetramethylsilane, will give you a value of 0, and as you go to the left, then the number will be higher, and the number will give you information about the chemical environment of the different proton, which can help you identify your chemical structure or the organic structure. So what is the reference material, which is tetramethylsilane, and why is it used as a reference? So the location of the NMR signal in a spectrum is used or is located relative to the reference signal from a standard compound. This standard compound must have certain criteria, and these are that it must be chemically unreactive and it must give a single sharp NMR signal. Tetramethylsilane actually have a single sharp signal in NMR, and it's chemically unreactive. So, and also one advantage of tetramethylsilane, or why it's used as a reference, because the signal that is given by tetramethylsilane is the signal that is given to the far right of the spectrum, and no other proton or no other signal can be to the right of that one. So this is why it's taken as 0, and everything else is relative to the signal given by the tetramethylsilane. And the chemical shift that's given to the other protons will have units as part per million relative to the signal from the standard, which is a tetramethylsilane, and it will give it a symbol, which is the this sample, which is the chemical shift or the part per million. So interpretation of the NMR spectrum. So what information can we get from the NMR spectrum? There are four things that we look for in an NMR spectrum. First thing is the number of signals, then the chemical shift and the relative intensity, and finally the shape of the signal. So the number of signals in the spectrum will give us information about the number of chemically non-equivalent nuclei. What do we mean by chemically non-equivalent nuclei? So if you have several protons or several hydrogens which have the same chemical environment, meaning it have the same surrounding, the same connection, then these will give one signal. So if you have more than one signal, that means you have more than one non-chemically equivalent nuclei. So let's have some examples. So if you have something like this compound here, you have the the benzene ring and two methyl groups, you would expect to have only two different signals. The first one will come from the 6 protons from the two methyl groups because they are exactly have the same surroundings, so they will all give the same signal. And then the 4 protons on the benzene ring, they will have the second signal, so you will only have two signals. The second compound here, as you can see, we also expect to have two signals. One signal from these 6 protons here because they have the exact same chemical environment, they have the same connections, and then these two protons here on the left, they have different chemical environment because the carbon they attach to have a chlorine atom attached to it directly, so they have different chemical environment. This third compound, which is the methyl ethanoate, you have the methyl group here, or the 3 protons on the methyl group from the alcohol here. That will give you one signal because they are exactly the same. And then the 3 hydrogens on the from the ethanoic acid, they will give you a different signal because the chemical environment is different. These 3 protons are attached to a carbonyl group, while these 3 protons are directly the carbon directly attached to an oxygen, so they will have two different signals. So you can apply the same principle, and then you can find how many different chemically non-equivalent nuclei there are. And then there is the chemical shift. The chemical shift will give you more detailed information about the chemical environment of that particular proton that gave you the signal. So what is the chemical shift, and why should the proton nuclei in different compounds behave differently in the NMR spectrum? Electrons surrounding the protons are charged particles, and they move in response to the external magnetic field. The electrons will generate a secondary magnetic field which is opposite to the external magnetic field. So the secondary magnetic field will shield the nucleus from the applied field or from the external magnetic field. So if a proton has a high density of electrons around it, surrounding it, then we expect it to be more shielded from the external magnetic field, and it will need less energy for the flip, or that will absorb less energy to cause the flip of the spinning of the nuclei from being with into being opposite to the external magnetic field. So this is why, based on the chemical environment, what atoms surround that particular the nucleus or that particular proton will give you a different chemical shift. So let's have some example here to understand this more. So if we have these different compounds here and we are trying to look at the chemical shift for the methyl group or for the three protons from the methyl group for each. So now we have tetramethylsilane. This is the reference compound, will give us a peak at 0, chemical shift 0. And then we have the methyl here in ethane, and this is not this is shielded by the electrons because there is no groups or atoms that actually pulls the electrons away from these protons. There is two methyl groups attached to each other, and we know that the methyl group will actually have positive inductive effect, so they kind of push the electrons towards the center of the molecules or away from them. So now we're gonna have the chemical shift of the ethane more closer to the methylsilane. And then we're going to have this one which have these three other compounds. They have attached to the carbon or to the methyl group. We have an electronegative atom. These electronegative atoms are nitrogen, oxygen, and fluorine. So the nitrogen is less electronegative than oxygen, which is less electronegative than fluorine. That means the nitrogen will pull the electrons away from the methyl, but and cause some deshielding of the nucleus of the hydrogens or of the proton or of the three protons from the methyl group, but this is going to be less than the deshielding that we see with the oxygen, which is again going to be less than the deshielding that we see from the fluorine. This is why when we have the nitrogen, you're going to have the chemical shift at a bit shifted to the left, so more like 2.2 part per million, and then when you have the oxygen, it's 3.2, and when you have the fluorine attached to it, it's 4.3. So the more the electronegative the atom attached to the carbon, which is next to the hydrogens or the protons that give you the signal, the more deshielded the protons and the more the signal is going to be to the left. In your exam, you will be given data, or you're going to be given a table with the expected chemical shift for different proton, but it's usually very important to understand why the different protons give you this particular chemical shift. The third thing that we look at in the NMR spectrum is the integration of the peaks. So the integration is the area under the peak for each signal, and it will give you information about the number of chemically equivalent protons that give you that particular signal. So for example, if we have compound like that, we expect to have three signals because we have three different non-equivalent protons. So signal 8, A, comes from these three protons, and the signal B comes from these two protons, and then signal C comes from the five protons on the benzene ring. And so the number of protons or the integration here is going to be 3 to 2 to 5, or it could give you an arbitrary number where the ratio between these three numbers will be 3 to 2 to 5. Usually in your exam, they will give you exactly how many protons are responsible for that particular signal. So that will give you information about the number of chemically equivalent protons that give you the signal. And finally, spin-spin coupling. Spin-spin coupling will give you information about the number of protons on the adjacent carbon. So if you have a signal for a certain proton and this signal is split, then this splitting pattern will give you information about how many protons are there on the adjacent carbon. So let's have some examples to understand that. So if you have a compound like 1,2-dichloroethane, so you expect to have only one signal. We expect to have one signal because all the four protons are chemically equivalent, so you have one signal. And this signal will not be split because these are chemically equivalent protons, and chemically equivalent protons do not split the signal for each other. However, when you look at compound like this one, which is 1,1-dichloroethane, then you expect to have two different signals. One signal for the three protons on the carbon on the left, and one signal for the proton for the carbon on the right. So the three protons for the which are chemically equivalent on the carbon on the left will have one signal, and this signal will be split by this one proton on the adjacent carbon, which is non-equivalent, non-chemically equivalent to the other three protons. And we expect to see the splitting as doublet because the splitting is actually n plus 1, meaning you need to see how many protons are chemically non-equivalent on the adjacent carbon, and that will split the signal for the other protons with n plus 1, which means the number of these protons plus 1. On the other hand, this proton here on the right hand side will be split by the three protons. Applying the principle of n plus 1, it will give you 3 plus 1, so it will be split into four signals. So it would be four small signals. So it will not be a singlet, but four small signals because this is a splitting relative to the number of protons on the adjacent carbon. So a signal split by n equivalent protons is split into n plus 1 peaks. So if the number of equivalent proton causing the splitting is 1, that will give you 2. The split the peak into 2, so it's called doublet. If it's 2 protons, it's going to be 3, so triplets, and so on. Remember that coupling, spin-spin coupling, only takes place with chemically different protons, not chemically equivalent protons. Also, it will not take place between protons on the OH or of the hydroxide part of the molecule or of the OH. So if the adjacent atom is oxygen and there is a hydrogen attached to it, this hydrogen will not split the protons on the adjacent carbon. So to see if a hydrogen is chemically different, you need to look at the whole structure of the molecule, not just the neighboring atom. So let's have some examples. So this is butane. Butane has 4 carbon atoms, and we expect to see 2 signals for butane. So one signal for the 2 methyl group, or for the 2 um, um, 6 hydrogens on the carbon number 1 and carbon number 4 because they are chemically equivalent, and a second signal for these 4 protons for the CH2 and CH2, these 4 protons. So we only see 2 signals. And then for the splitting, you can see that the CH3, adjacent to it, there is a carbon which has 2 protons, which are non-chemically equivalent to the protons on the CH3. So this is gonna split. So the CH3 will be split into a triplet because there are 2 protons here adjacent to it. On the other hand, the CH2 and CH2 on carbon 2 and 3, they are chemically equivalent. They will not split each other. However, adjacent to them on the other side, there are 3 protons on the adjacent carbon, and each of these 3 protons will split the signal of the 2 protons into a quartet, or as split into 4. Another molecule here is ethylene glycol or 1,2-ethane diol. We expect to see two signals. One signal due to the four protons on the CH2 and CH2 because they are chemically equivalent, and one proton for and one signal for the two OH here. But there will be no splitting because the proton on the oxygen will not split the protons on the carbon and vice versa. Also, the protons on the carbon will not split the proton on the signal that comes from the proton on the oxygen. So we will see only two signals, one due to the CH2 groups and one due to the OH groups. An example of a molecule and the what we need to look for and the spin-spin coupling. So if you have a molecule like this one, 1,2-dipromo propane, 1,2-dipromo-propane, we expect to see three different signals, one for the CH3, one for the CH2, the two proton on the CH2, and one for the hydrogen on the carbon number one, which has two bromide atoms. Now for the splitting, looking at the CH3, this is the most shielded one. So this is going to be the one on the right hand side of the spectrum. And this is going to be, of course, the integration is three protons. And for the splitting, there are two protons on the adjacent carbon. So that will give us a triplet. So this is the signal that comes from the CH3, and this is three protons. And then these two hydrogens here on the carbon CH2, there are three protons on the left hand side and one proton on the right hand side. So in total, there are four different protons that will cause the splitting of these two protons. So the number of split will equal n plus 1. So the total number of protons here is 4 plus 1, so will equal 5. So this signal here is the second one, and this is going to be a bit more shielded, more deshielded than the CH3. And finally, this proton here on the carbon number one, this is the most deshielded because of the two bromide group on the carbon, and the two bromide group are electronegative atoms, and they're gonna pull the electrons away from the hydrogen, and then this is why it's a bit to the left on the spectrum. And then about the splitting, you can see that this proton here adjacent on the adjacent carbon, there are two protons, so there is going to be n plus 1, so n here is 2, so 2 plus 1 is 3, so it's going to be a triplet. And the integration is 3 and 2 protons, and then here is 1 proton. Carbon-13 NMR also can give you information about the structure of your organic molecule. And the carbon-13 NMR, the signals will be due to the carbon, not due to the hydrogen atom or the hydrogen nuclei. And in carbon-13, you wouldn't see spin-spin coupling, and also you will not be able to integrate the signals to find the number of equivalent carbon that is responsible for the signal. So you will only see singlets for all of the signals, and also the height or the area under the peak will not give you information about the number of carbons that give you that particular signal. But you're going to apply the same principles for the chemical shield, for the chemical shift, and the chemical and the shielding of the protons of the carbon. So the presence of electronegative atom adjacent to the carbon will shift it more to the left. The ones that are shielded by electropositive atoms, then it's going to be more to the right. And for the NMR, for the carbon-13, the chemical shift can reach up to 220 part per million. However, for the proton, it's a maximum of 14. A quick example of proton NMR for a different compound and how to differentiate between them based on the splitting and the chemical shift. If we have something like ethyl, like methyl like ethyl acetate or ethyl ethanoate. So ethyl ethanoate, we have a total of three expected signal. One for that three protons on the from the ethanoic acid, and then these three here from the ethanol, a part of the ester, the CH3, and one for these two protons. So which one will be the most shielded? The most shielded will be these three protons here on the ethyl side of the alcohol of the ester. So there will be these three protons. The splitting of these will be a triplet, and this is going to be three protons. And then following that, we have these two protons and we have these three protons. Which one will be more deshielded? Which one will be less deshielded? Of course, because these two protons have oxygen just adjacent to the carbon, they will be more deshielded than these three protons because there is a carbonyl group, not an oxygen directly attached to the carbon. So the second signal that we see is for these three protons, the green ones, and these going to be a singlet because there is no adjacent on the adjacent carbon there is no protons. There is only a carbonyl group. So this is going to be a singlet and there are three protons. And then finally the two protons here for the ethyl group and for the CH2 on the ethyl group, and these are the most deshielded, and it's going to be split by the three protons adjacent to it, and this going to be a quartet. So there are two protons here which are a quartet. So this is the NMR for the ethyl acetate or ethyl ethanoate. What if we have methyl propanoate? Methyl propanoate also we expect to find three signals. One for the CH3 from the methyl group for the methanol of the ester, and then of the alcohol of the ester, and then we have these two signals from the ethyl, the CH3 and the CH2. Now, which one is the most shielded? It's this CH3 here on the left hand side of the propanoic acid. So the CH3, it will give you a signal here on the right hand side. It's going to be split by the two protons on the adjacent carbon, and it's going to give you a triplet. So a triplet with three protons. And then the second one is going to be this this CH2, not the CH3 on the alcohol. So the CH2 will give you a quartet because it's going to be split by this CH3 here, the three protons on the left hand side, and the signal, this is the signal by the two protons, so this is two protons and a quartet. And finally the CH3 of the alcohol, it's going to give you a singlet because there is no adjacent protons on the or the carbon, there is no carbon or the atom adjacent to it that doesn't have any protons, so there is no splitting, and it will give you a singlet, and this is three protons. So this is the difference between these two and how you can find the structure based on where to find your signals on the spectrum.